Hey everyone, and welcome to another exciting edition to Big Ideas Algebra 2. We're in Chapter 3, 3.2, Complex Numbers today. So complex numbers, and we're going to see what those are, and we're going to see what an imaginary number is. We're going to be adding, subtracting, multiplying, doing all the operations with these complex imaginary numbers. All right, well, but first, let's go ahead and do a little cartoon of the day. Gabrielle, Grace, what did I tell you kids about playing soccer in the nest? Well, in the bleachers cartoon, they have nowhere to go with that soccer ball there. Okay, so on page 50 in your notes, we'll see this like little, kind of tree diagram here. It starts off with complex numbers on the top. It breaks that into two. So complex numbers are broken into two parts here, which is real numbers and imaginary numbers. And there's nothing else under imaginary numbers, but under real numbers, that's where we've been in math all along. So we've only ever touched this real numbers side. And real numbers break into two parts here with rational numbers and irrational. There's nothing else under irrational, but under rational numbers we find our integers, our whole numbers, and our natural numbers. So let me just go over these, and you can just write these down. What are these all about? What is natural numbers? You may have forgotten. Natural numbers is just your counting numbers if you start with 1. So, it's like if you were playing hide and seek. Go count to 100. 1, 2, 3, that kind of thing. You're going up to a positive infinity. That's natural numbers. Whole numbers would be almost the same thing except you start with 0. So if you were to start with 0, 1, 2, 3, it's all that side of starting with 0 of a number line. So 0, 1, 2, 3, and so on all the way to positive infinity. Whole numbers. Integers, that's where you have both sides of the number line. So you have your positive side like the whole numbers, but then you also have your negative side. So from negative infinity to positive infinity, you got your negative 1, negative 2, negative 1, 0, 1, 2. Now you notice there are no fractions in here as well, so you're all just still counting numbers. But now you have the negative side and the positive side with 0 in the middle. Your rational numbers, that's where you will now see your fractions, your decimals. So rational numbers includes fractions, so like 1/2, 1/4, 2/3, those kind of things, those are rational numbers, and also terminating and repeating decimals. So a terminating decimal would be like it stops at your 10th or your 100th or your 1000th place, and it terminates at that decimal number or that decimal place. Or it could also be a repeating decimal, which would be like 0.3 repeating. That's like a 1/3 is 0.3 repeating. So those are our rational numbers, and rational kind of thinks that you can understand them. Irrational numbers would be numbers that we kind of don't understand, which in that case would be a decimal that doesn't terminate and it doesn't repeat. So it has no pattern. So if it's that kind of number, that would be a number that if you took the square root of some number. So if I was to take, let's say, a calculator here, and I said, okay, 4 and hit the square root button, that gives me a rational number of 2. But if I put in, let's say, 5 and the square root button, that gives me a number that doesn't repeat, and it will never end. Even though it does look like it ends at the 8 here, it actually will never end. It will just keep on going. So really, irrational numbers are square roots of non-perfect squares. It's a square root of a non-perfect square. So it's something like an example would be the square root of 2. 2 is not a perfect square, so the square root of 2 would be an irrational number. All of those are under the real numbers. These are all real numbers, everything over here on this side. Then we have on this side imaginary numbers. Imaginary numbers where we deal with the square root of a negative number. That's what we're going to deal with on this one. So imaginary numbers deal with square roots of negative numbers. You can see that's what it says. The imaginary unit I is defined as the square root of -1. And down here I wrote it here. The square root of -1 is I. They're going to use I as standing for imaginary. So every time we see the square root of -1 here like this, we're going to be able to change it to I. And if we see I squared, okay, if we were to square I, now since I does have a value, I is the square root of -1, if we were to square this square root of -1, it would remove the square root sign. It would undo the square root sign. It would just be left with 1. So this is also an important one to remember. Every time you see I squared, it is going to equal -1. So these things we have to keep in mind as we're going through this lesson. Okay, so on page 52 of your notes, the vocabulary, if you didn't already put down that thing from the last screen, you want to put it down here under imaginary unit I. You can just put what we had there as the square root of I, -1, square root of -1, which is this, is I. So you can show that right there. This would be the imaginary unit I. So that would be what we're talking about right there. And then if we do this one, I times I is I squared. If you multiply an I times an I, you're going to get I squared. Just like if you did X times X, it's X squared. So I does work like a variable. It just has a value. So we don't actually consider it a variable because it does have a value to it. It equals the square root of -1. But it works, you know, because it's a letter here, I, it works like a variable. And so we can see that when we see I squared, we're going to get -1. So here's what I'm talking about. If you were to square, you know, I squared is the square root of -1. I is the square root of -1. So if you were to square the square root, it's going to undo the square root sign, and that would equal -1. A complex number down here. So a complex number is made up of a real number and an imaginary number. So you can write that for complex number. It's got both parts to it. And you remember that the diagram you saw there, complex numbers was on the top, and it's broken up to a real and imaginary. So there's a real side and an imaginary side. So that really can be what a complex number is. It's made up of a real number and an imaginary number. So it could look like this: A plus BI. Now A and B would be numbers here. So A would be the real part. The imaginary part would be the BI over here. So you have your real part, your imaginary part with a plus or minus in between that. And then as far as an imaginary number goes, that's really just what this is, like this part here. This is the imaginary part, so that's the imaginary number. But let's take a look at this little, oops, there we go, little vocabulary right here. Complex numbers, we got the A plus the BI, that's what this is. But your real numbers are over here, that's like A plus 0I, which would mean that imaginary part's not there. So every real number could be considered a complex number here because you can always put it as some number plus 0I. And so that's why these are all numbers that would work. Or imaginary numbers here, you could see, you know, 2 plus 3I, 9 minus 5I. Those still are imaginary numbers. We can call them complex or imaginary. That would work either way. So you can say 1 plus 2I is an imaginary number. But if we just want to talk about a pure imaginary number, then that would be what this part is. The imaginary part here is the pure imaginary number. So if that basically means if your real part is 0, then there's no real part, it's only imaginary. So it's just a pure imaginary number, like 2I. So it'd be like 0 plus 2I is still just 2I. So it's a pure imaginary number. Okay, on this core concept, it says the square root of a negative number property. So here's our properties of doing this. So if we said, okay, if r is a positive real number, then, you know, square root of -r would be I times the square root of r. So the negative under the radical sign, that's like -1 times r. You could break that apart. And now you still have the r underneath, but the -1 will come out as an I. So like there's an example, the square root of -3 would be I square root of 3. Since 3 is not a perfect square, it's still going to remain under the radical sign. But now we can take out the negative and put an I in front of this to show that this is an imaginary number. By the first property, it follows that if you square this, so if we were to square this, we're just going to go back to -r. And so same thing here. If I was to square this, it's like squaring I and squaring the square root of 3. I squared would be the -1 times 3, because if you square a square root, that's going to undo the square root sign. And so it's -1 times 3, which would be -3. All right, so on the bottom of page 52, underneath this core concept here, here's 4 problems. Let's look at the first one, then I'll have you do these 3. So the square root of -4, what would that be? Well, we first can see that we can break apart -4 to +4 times -1, and then the square root of each individually. So we could then say, okay, the square root of 4 times the square root of -1, and we know the square root of 4 is 2, the square root of -1 is going to be the letter I for imaginary. So the answer there would just be 2I. So you can quickly, you don't have to do all this part, but you can quickly see that if it's got a perfect square here, it's going to be that number. The square root of 4 is 2, but if it's negative underneath there, you're going to say that's an imaginary number, though. So it's 2i. So the square root of negative 4 is 2i. Go ahead and do the next 3 here. Pause the video real quick and write these down and answer them, and just check your answers to see if you got them correct. See if you understand this. Okay, so hopefully you've copied these down. You have answers. Hopefully you're checking for your understanding here to see, did you understand what this was talking about. So the square root of negative 25, well, we know the square root of 25 is 5, but because it's negative, it is going to be 5i. Same thing here. The square root of 49 is 7, but since it's negative, it's going to say 7i. And this one, 13, is not a perfect square, so that's going to remain under the radical sign. But because it's negative, we're going to pull out the negative sign and turn it into an I. So it's going to be square root of 13 times I. Now they put the I back here. As you notice up here, they put the I in front. I usually like putting the I in front, though, just so that it doesn't get confused. I is not under the radical sign, because sometimes these radical signs have a mind of their own and they get a little long here. We don't want to think that that I is underneath the radical. It needs to be outside of it. So typically, I think the best thing for you to do is keep those I's in front, like the example in this core concept shows you. All right, now as we start our extra practice, 1 through 6, it says find the square root of the number. This is on page 53, and number 1 is the same one we just did, so you can just go ahead and copy that down again. We know the square root of negative 49 is 7i. I stands for imaginary number. We also did this one, square root of negative 4. We did that one. You can copy that one down as well. That's 2i, so you already know those. We did those just a second ago. Number 3, however, now this one has a negative, so it's going to have an I coming out, but 45. We want to break that apart and see, okay, is there any perfect squares in 45? So we got to think of it as really 3 things. 9 goes into 45, which is a perfect square, so 9 times 5 times a negative 1. So we have a 9, a 5, and a negative 1 all separated there. And we could take the square root of each one. The square root of 9 would be 3. The square root of negative 1 is I, so that's going to be 3i in front of your square root sign, and 5 should still be underneath the radical. So here's what the answer should look like. 3i in front with the square root of 5. Number 4. This one already has a negative 2 in front, so we're going to maybe multiply whatever we pull out of this radical here. We're going to be multiplying it by the negative 2. Well, obviously, we know the square root of negative 100 should be 10i. So if I say, okay, 10i times negative 2, that should be, so I multiply negative 2 times 10i. Negative 2 times 10 is negative 20, so the answer is just negative 20i. On number 5, same thing here. This is going to be 121. It's a perfect square number. That's 11 times 11. So since it's going to have a square root of this is 11, but it's negative, so it's negative. It's not negative 11. And that's what a common mistake would be, to say, okay, the answer for this is negative 66, because you think, okay, this is negative 11, and then you multiply negative 11 times 6. That's not the correct thing. Just because there's negative underneath here doesn't make your answer negative. It makes your answer imaginary. So you got to make sure that's very clear and you understand that when you have a negative under the radical, it's an imaginary number. You're going to give an I, the letter I, to that number. So this is 11i, so it's going to be 6 times 11i, which will be 66i. Here's number 5, or number 6. It has a 5 in front. We're going to do the same kind of thing as we did with this negative 45. And whatever we pull out, we're going to be multiplying it by 5. So think about what perfect square would be in 75. And hopefully you're thinking of the number 25. 25 goes into 75 3 times. So we'll say, okay, 5's on the outside. The square root can be broken up to 25 times 3 times negative 1. Square root of 25 is 5. Square root of negative 1 is I. So that's going to be 5i times this 5 here. So 5i is going to be times the 5. Square root of 3 is still there. 3 is still under the radical sign, so we still do have a radical in our answer, but 5 times 5 here is 25, so it's going to be 25i on the outside with a square root of 3. Okay, so on problem 7 and 8 it says find the values of x and y that satisfy the equation. Now these are kind of weird looking equations here. It's got an x, a y, and an I in this equation. And we need to remember when we see the letter I, that does stand for imaginary. So that would be the square root of -1 for those. And these equations here are kind of just a little strange. There's not much to do with them, but they're very easy to actually solve. What you're going to do here is you're going to put basically the real parts together in one equation and the imaginary parts together in another equation. So the real parts will equal each other. So this would be a -10 with an x here, but -10 is real. It doesn't have an I with it. And then this 30 on the other side is also real, so this -10x is going to equal the 30. Those would be the real parts. Those are going to equal each other for one equation. The other equations, you're going to put the imaginary parts equal to each other. So you have an I on this equation and a -yi on this side. So the y is the one that has the imaginary. X is real, y is imaginary. And so you're going to say I is equal to a -yi on the other side. So you made just two equations from this one to solve for x on this side, to solve for y on this side. So as we solve these real parts here, it's just quickly going to be dividing out the -10 first. And so then these cancel here. 30 divided by -10. X is -3, so that was easy. This side over here, we want to divide out an I. Okay, I want to get y by itself, so I'm going to divide by I. So I divided by I is still going to be 1. Anything over itself is equal to 1. So this is going to be 1 is equal to -y, because our i's will cancel. So 1 is equal to -y. And then we just need to change the sign. Multiply this by a -1. Multiply both sides by -1. So negative times negative is positive y. That makes that -1 on the other side. So y is equal to -1. All right, number 8, same thing. You're going to go ahead and put the real parts together. So we're going to have something like this. I'll do it like this. Real on one side, imaginary on the other side. Go ahead and pause the video. See if you can write the two equations here and then solve each one to find x and y. Okay, so hopefully you got an answer for x on this side, you got an answer for y on this side. So our equation first is going to be the real number 44 is equal to the real part here with the x, -1/4 x. So that's your first equation for the real. The imaginary is the one that's going to have the i's with it, right? So this is a -1/2 yi. That part is equal to the -7i over there. So there's your other equation. So once you have these two equations, you're just going to solve for the variables. For this one, x here, it's a 1/4. We want to get rid of our fraction by multiplying by 4. And we need to multiply also by a -4 because we want to make this a positive x. So we'll multiply both sides by -4. That's going to cancel the 4's, cancel out the negative signs, leave me just with x. -4 times 44 is -76. So there's your answer for x. And then for the imaginaries over on this side, we want to also cancel out the fraction here. We want to multiply first both sides by a -2 to cancel out the 2 here and the negative sign from the y term. So as we multiply first by -2, so those cancel there. This becomes a positive 1 yi. So we're just going to have a yi on this side is equal to -2 times -7. It's 14i on the other side. And now I just need to get rid of my I by dividing both sides by I. And when I do that, it gets rid of the i's on both sides, so y is just equal to 14. So there's your x is -176 and your y is 14. So not too hard. Hopefully you understood how to do that, and you can do those on your own when it comes to the assignment. Okay, so now we're going to start to do some operations with these complex numbers, starting with adding and subtracting. It says the core concept here, sum and differences of complex numbers. This is on page 53, and you can see what it shows you here, the sum of complex numbers. You're just going to combine the real parts together, a plus the c, combine the imaginary parts together, the b and the d with an I, and that's all it is. The same thing with subtraction. You're going to subtract the reals, subtract the imaginaries. So here's a couple examples right underneath this core concept on the notes section. Go ahead and write these down. A and B. So it says 3 plus 5i plus negative 2 plus 3i. So we're going to put our real parts together first. In fact, go ahead and write this down as well. When you add or subtract, an easy way to remember it is really just you're going to combine like terms. And that's kind of what we're doing. We're combining like terms here. So if we can kind of pretend for a minute that this is like an x, if it was a variable and we were to add these together, we would just put 3 and negative 2 together and these terms together because those are like terms. So it is, adding and subtracting complex numbers is just like combining like terms that you should have done in Algebra 1, even in pre-algebra. So we start with these 3 and negative 2, put those together, 3 plus negative 2, and then you're going to have the 5i combined with the 5i and 3i, adding those together, 5i plus 3i. So this right here is 1, and over here is 8i, so our answer is just 1 plus 8i. On B, we're going to see the 6. Now it's a minus 1 here, so we're going to still put these together, but with a minus. So it's going to be 6 minus 3 for the real parts. And then the imaginary parts, 4i minus 6i. We'll be putting those together. And as we do that, we're going to get 3 here, and we're going to get negative 2i here. So 3 minus 2i is our answer. That's our complex number. It's the real part's 3. The imaginary part is negative 2i. Okay, let's go on to the extra practice for these problems. Okay, so on page 54, here it says simplify the expression 9 through 12. We're going to classify, so we're going to just do 9 through 12 right now. Classify the result as a real number or imaginary number. Then if the result is an imaginary number, specify if it is a pure imaginary number. So first of all, just go ahead and add these together, or add or subtract them. That's what 9 through 12 is about. I'm going to give you a chance to do that, so go ahead and pause the video. Try 9 through 12 on your own. See if you can just add and subtract, combine the like terms, get the new number that you're supposed to be. It could be an imaginary number or pure imaginary or even a real number perhaps. And if it is, go ahead and you can write down which one that is as well. And then play the video and see how you do on this 9 through 12 and if you understand how to add and subtract these complex numbers. Okay, so hopefully you paused it already and now you have answers for 9 through 12. Let's go ahead and check those and see if you understood what you're doing. Okay, so hopefully you paused the video and you've done 9 to 12 and then you're just checking to see if you get these correct. So for 9, we're going to be putting the real parts together, which is negative 8 plus the negative 1, and the imaginary parts would be 3i plus negative 2i. So we're going to see that become negative 9 from the real parts, and these two combine to give us a positive 1i, or just positive i. So there's our number. What we would call that would be imaginary, or we could even call it complex, but that wasn't really one of the options up here. So really just it's an imaginary number. It's not pure imaginary because it does have both parts, real and imaginary, still with it. Number 10, so we got 36 minus 12 for the real parts, and then negative 3i minus 24i for the imaginary parts. So 36 minus 12, that's going to give us 24. These will combine to give us a negative 27i for that part. So 24 minus 27i, and that is also imaginary, just like this one is. It's got both parts, real part, imaginary part, which means we can just call it imaginary. 11, we're going to see 16 plus a negative 16 for that one, which would be just 0. And then 7i here, because we're going to get a positive 1 and negative 8. So take 1 away from negative 8, it's going to give us a negative 7i. So 16 plus negative 16, those actually cancel out or makes 0. So since this is 0, there is no more real part, which your answer then was just going to be negative 7i. And so since there's only the imaginary part, we can call that a pure imaginary number. So it's not imaginary because it doesn't have a real part anymore, so we can just call it only pure imaginary. And then for 12, we're going to see negative 5 minus negative 6. So that's a double negative. We want to change that to positive. And then we're also going to see for the i's, negative 5i minus negative 6i. So also double negative here as well, changing that to positive. And so when I put these together, this is going to be 1. And over here, this is going to be a 1i, or just I. So it's just 1 plus I, which that would be imaginary. So the only one that was pure imaginary was this one here. There was nothing here that was just real. The only way it would be real is if the imaginary parts canceled each other out and you only left with a real number, then that would have been real. Okay, so for our joke of the day, question is, where do cows go on the weekend? Where do cows go on the weekend? To the movies. Movies. Okay, so the next two problems, 13 and 14, on the extra practice are now multiplying two complex numbers together. And I wanted to do a couple examples. First, over on page 52, again, just at the bottom of page 52, there should be some more space for you to write this. So just write A and B over there, and let's do these here, and then I'll have you try 13 and 14 on your own. For letter A, we have 5 plus 3i times 2 plus 7i. So to multiply two complex numbers, it's the same as like multiplying two binomials. So you can use FOIL. And if you remember FOIL, it just stands for first, outside, inside, last. It's a quick little easy way to remember how to multiply two binomials together. So your first terms would be 5 times 2, which that would give you 10. Your outside would be the 5 times the 7i, so that's going to give you 35i. The inside two terms would be the 3i times 2, and that's going to give you 6i. And then your last ones would be 3i times the 7i, and that's going to give us 21i squared. When we do I times I, it still is I squared. Now there's another way we could do this other than FOIL if you prefer it. Maybe you've done this before. It's called the box technique, and you can go ahead and put one of the complex numbers or the binomials on top like this. So this column is the 5, this one's the 3i column, and then the other one goes down the side, so the 2 and the 7i goes here. So you have your 2 row and your 7i row, and then just see what you can multiply. 5 times 2 there is the 10, 2 times the 3i there is 6i, 5 times the 7i right there is 35i, and then the 3i, 7i combines in that last one is the 21i squared. So you can get the same four terms as we got here with the box technique. So it doesn't matter which technique you like to do better, just continue to do the one that works for you. So now as we start to work on this, now if we did this, we want to put it back into kind of a row like this. We want to combine our like terms together, these i's. So we start off with 10, 35 plus the 6 for combining like terms is 41i, and then 21i squared. Remember, I squared is something special. That always equals -1. And so here's where we see an application of that, 21 times -1. And so now as we continue to simplify, we're going to get the 21 times -1 is -21. So we're going to get the 10, the 41i, and now minus 21, and we can put these two like terms together, the 10 and the -21, so that way our answer is going to be -11 for the real part and 41i for the imaginary part. So that's our final answer. Your answer will always end up being a complex number, a real part and an imaginary part, whenever you're multiplying or adding or subtracting, doing any operation with complex numbers, you're going to get a complex number, or you could get a pure imaginary number, or you could just get a real number as well. But it's not going to have more than two terms, that's for sure. Letter B, let's look at this one, 3 plus I, 3 minus I. So this would be considered a sum and a difference because they're almost exactly the same. One's a plus, one's a minus. But when we talk about that in imaginary or complex number terms, we can call those conjugates. That's the name we actually call these. So you might be asked to find the conjugate of something. These are conjugates of each other because the conjugate of 3 plus I is a 3 minus I. Or the conjugate of 3 minus I is a 3 plus I. These are conjugates of each other. That's what we would call these. These are conjugates. And if you ever have that situation where you're going to multiply conjugates, it actually is a little bit easier than doing all four of these. You only have to do the first and the last only, F and L only. So that would be doing just the 3 times the 3 and the I times the negative I. So as we do that, 3 times 3 for the first is 9, and I times negative I would be a negative I squared. And there's an application of I squared where we need to change that to -1. And so now really it's going to be 9 times, or 9 minus -1. and we see a double negative happening here. So that's going to become a plus. 9 plus 1, the answer will just be 10. So our answer is 10, which means this is going to be a real number. So we have an imaginary number on this answer, but this is a real number only. All right, so now come down to 13, 14 on page 54. Try these two, multiply them just like I showed you here with FOIL or the box technique, or if it's conjugates, you can just do F and L only. If you didn't really realize it's conjugates and you still did FOIL, you still could get it correct. But go ahead and pause the video, do 13 and 14, and then play it to check your answers. Okay, hopefully you finished 13 and 14. Let's go ahead and check your answer for these two. So for this one, I'm just going to use FOIL. So I'm going to multiply -1 times 15. That's going to be -15. And then the outside is going to be -1 times -I. That's going to be a positive I, plus I. Inside, it's 9 times 15 with an I. So it's going to be positive, because positive times positive will give us positive. 135 times I, and now negative times positive here will be a negative sign, and it'll be a 9I squared for that last one. And now we're going to start putting things together. So -15 still there. These will combine to a I keep saying the sign wrong, positive 135I. So it's going to be positive 136I. Sorry, I keep messing this up. So yeah, we have 1I plus 135 is 136 with an I. And now over here we have an I squared, which you need to remember that's -1. And so this is really 9 times this -1, which will become a positive 9 there at the back. And then we want to just combine our real numbers here. So add 9 to -15. You're still going to have a negative real part, but it's going to be a -6 plus the 136I. So there's our final answer, and that is an imaginary number. So remember, we still need to label this. Is it imaginary or real or pure imaginary? It's just imaginary because it does have a real and imaginary part. Then for 14, maybe you noticed that it was conjugates, because that's what this is. 13 plus I, 13 minus I. It's the same thing except one's plus, one's minus. So you can just have to do 13 times 13 and the I times the -I. So 13 times 13 is 169, and then that would be given -I squared when you multiply these two, and I squared is -1, so it's 169 minus a -1, and that becomes double negative, so this becomes a 170. So 169 plus 1 is 170, and that would just be a real number only, so you can label it real on this one. Okay, so before we get to number 15, which looks like this figure right here, I wanted to explain what this was, because if we just talked about 15 without doing this, you would be very lost on really what this thing is. So let's go and read through this so we can understand it. And really what this is a little bit of electronics. It's an electrical circuit component. So electrical circuit components, such as resistors, inductors, and capacitors, all oppose the flow of current. This opposition is called resistance for resistors. That makes sense? And reactance for inductors and capacitors. Each of these quantities is measured in ohms. So ohms is a unit of measure. So it's like, inches or centimeters, but in this case we're talking about electrical currents, so it's considered ohms. In fact, if you were to stick, there's an ohms meter, in fact, that you can buy at a hardware store and probably Walmart as well, that you would stick it into your electrical sockets that you plug things into to see how many ohms it's producing. So that's something that you could do, and it's an ohms meter, they call it. The symbol used for ohms is this, looks like a horseshoe, but it's actually the uppercase Greek letter omega. And so this little chart here says, okay, we got the component symbol, we have your resistor, the capacitor, the inductor, and the capacitor. So this side over here would be your inductor, this side over here is your capacitor, and your resistor, I believe, is just up here on the top here, and it didn't do the little squiggly, but that's what the resistor would be. So R, L, and C is resistance or reactance in ohms. They're using letters here to represent this, like variables. And then impedance in ohms. R, L to the I, L times I is imaginary number still, -C times I as well. So this table here shows the relationship between a component's resistance or reactance and its contribution to impedance. A series circuit is also shown with the resistance or reactance of each component labeled. The impedance for a series circuit, this is a series circuit here, so we're talking about the impedance for a series circuit, is the sum of the impedances for the individual components. So that would be these here. So we need to realize that when we see this, this thing here, it's called the inductor, okay? It's an imaginary number for impedance. And this one here, which is called a capacitor, it's also an imaginary number for impedance, but it's actually a negative. It's a negative and it's imaginary. This one's positive and imaginary. This would be actually a negative and imaginary. The one here, the resistor at the top here, is just a real number. R, you could even stand for real. So this one at the top here is going to stay a real number. And so what it is the impedance for a series circuit is the sum. Sum means we got to kind of add these all together, combine them together, or combine like terms, just like we were adding the sum of the complex numbers. So it's the sum of the impedances for the individual components. That's these three components here. So we're going to add basically those three components, but you have to realize this is an imaginary, that's imaginary, so those will be combining like terms with these two. This is just going to be a real part up here. It says find the impedance of the circuit. So that's what we're doing down here. So the 5 up on top here is really just 5 ohms. Okay, the 3 here is really 3I ohms, and the 4 over here is a negative 4I ohms. And so as you put the negative or the i's together, that's going to become a negative 1I. So it's really going to be a 5 plus or a 5 minus I in ohms. 5 minus I ohms. Hopefully that now, as we go to number 15, that will make sense now when you see that problem. Okay, so now as we look at number 15, it makes a little more sense to understand that this is a series circuit. Find the impedance of the series circuit. So now these things make sense here. We need to know these horseshoes is just the symbol for ohms, which would be like the IN is for inches, CM is for centimeters, this thing is for ohms. And we also realize that we have our different things here. You don't really need to remember the names. You know, this is a resistor, inductor, capacitor. But you just need to remember which ones are real, which ones are imaginary. So the top one there is the real, the side ones are the imaginaries, and also which one for out of these here with imaginaries is positive and negative. So the one on the left is positive and the one on the right is your negative. So this would be a positive 10I, this is a negative 14I. So as we now going to say, okay, to find the impedance of the series circuit, we just need to add these together, take the sum of these three things. So you have your real number 5, and then you also have a positive 10I, and you have a negative 14I. So we just got to combine like terms here with the i's. So if I take 10 away from 14, that's negative 4. So we're going to see a 5 minus 4I, and we would just want to label that with ohms. We can just say, okay, it's in ohms. So that's our answer there, 5 minus 4I ohms. That's all that's talking about. It applies our complex numbers to a real situation. I mean, electricians. Somebody who is an electrician, if you call them out, they know about this. You can ask them about complex numbers and ohms and things like that, and they should be able to tell you something about it. 16 through 18 now is saying solve the equation. So we're going to solve these quadratic equations just like we did in the last lesson, except this time if we do get a negative under the square root sign, we're not going to say no real solution anymore. We're going to be able to have an imaginary solution then as well. So we will always be able to get a solution now at this point on, because we know that a square root of a negative will be an imaginary number. So you can see it's set equal to 0 on this one, which is a good thing. We would want to do that first anyways. And then we can see that, well, what would we do on this one? Well, we can see that's just got an x squared only. There's no bx term. Remember, we talked about that. We said there's a way you could do this with just square roots or factoring. We don't need to factor this one, even though we could. We still could factor this, but we might just want to use the square roots to do this one. So I'm going to subtract 25 from both sides first to get my 5x squared by itself. So I'm going to use the square roots method here. So I'm going to get the x squared by itself. I'm going to solve for x squared first, which means I still need to divide by 5 here to undo this 5. So now I have negative 25 equals 5x squared. Divide both sides by 5. That's going to leave me with a negative 5 now on this side, and is equal to x squared. So now to undo the square, we would take the square root of both sides. So we take the square root of both sides there. And at that point, we would see that we have the square root of negative 5, which if we want to think about that, we could break it apart to the square root of negative 1 times the square root of 5, and the square root of negative 1 is I. So this would be I times the square root of 5 for my x. But notice what I also added in here. Remember we talked about this on 3.1. Anytime you do the step of taking the square root of both sides here, you're going to add in plus or minus. In fact, you always do that if your root is even. When we even get to chapter 4, we're going to see, any even root's going to have to include a plus or minus. So a square root is an even root. So we have to put plus or minus I square root of 5 for our answer. All right, for number 17, it's not equal to 0, so we might want to do that first. Set this equal to 0 first by, well, we could have added 18. I suppose we could have done that to set it equal to 0. What I do notice, though, is that there is no bx. So there is no other x term in here, so if that's the case, then I don't need to set it equal to 0. I can just go ahead and solve for x squared, which is what I just did. So I'm showing you add 10, bring the 10 over this side, and now we just have x squared by itself, and it equals negative 8. Okay, so if this was a 10x, then I would want to bring the 18 on this side to make it equal to 0. So at this point, we would want to square root both sides, take the square root of both sides to undo the square here. And that leaves me with x. We're going to put plus or minus, because that's what we do when we do this step. And we have a square root of a negative 8. So if we put the negative with the perfect square, so if we think of it as negative 4 under the square root sign times 2. So the square root of negative 4 is 2i with a square root of 2. That will be our answer with a plus or minus in front of it. So x is equal to 2i plus or minus 2i square root of 2. We got to break this apart. We got to see that this 8 here has this perfect square in it. The 4 is a perfect square number. So I got to say 4i, or negative 4 is 2i for this one, and then we still have the square root of 2. Hey, number 18 has fractions. Now we always want to get rid of the fractions first if it's a problem like this. So to get rid of your fractions, it's always an easy step of multiply by LCD. That's always what you want to do. Multiply by the LCD, the lowest or least common denominator. So you got to think, you have a 3 and a 5 out of your denominators. What's the common denominator? Well, that would be where you multiply 3 times 5 and it gives you 15. So you're going to multiply this entire equation here by 15. Multiply each term in this equation by 15 to get rid of your fractions. So as we multiply this first term, the 3 will cancel with 15, but 3 goes into 15 5 times, so it leaves you with 5 left to still multiply the numerator by. So you have negative 1 times 5 times x squared. So that's a negative 5x squared for your first term. And then it's going to be equal to the next one here. 5 goes into 15 3 times. We cross out the 5. So there's still a 3 to multiply the numerator by. So 3 times 1 here is just going to be 3, so it's going to equal 3. And then 15 times the last fraction here. 3 goes into 15 again 5 times. So we're going to multiply the numerator here 4 by a 5. So 4 times 5 is 20 in front of x squared. So 20x squared. Now I want to get the x squareds by themselves. So I'm going to subtract 20x squared from both sides. And I'm going to bring that on the other side over here. So that's going to give me negative 25x squared equal to 3. And now at this point, we can, see what we're going to divide by negative 25. At this point, we'll divide by negative 25 to get the x squared by itself, because I only have an x squared. Notice there's no other x term. So these all three, 16, 17, 18, were all set up to be solved by using square roots. We didn't need to factor any of them. And so this is going to cancel out, leaving us with x squared, and it's going to equal this fraction here. So I have x squared is equal to negative 3 over 25. So we're going to take the square root of both sides. That's going to undo the square here. So it's going to be x is equal to, now the negative is going to be an I outside of a square root of 3. This numerator is still going to have a square root sign, The square root of 25 is 5 on the bottom, so that's going to become a 5 on the bottom. So our answer here is going to be one kind of ugly fraction. So it's x is equal to, the top you can say is plus or minus I squared root of 3, and the bottom is just 5. So you can kind of break this apart with the square root of 3 over the square root of 25. So the square root of 3 is I squared root of 3. We saw that one earlier. Don't forget your plus or minus though when you do this step, when taking the square root of both sides. And then the square root of 25 is just the 5 on the bottom. So that is our answer. We're going to enter it as that. All right, so that concludes our lesson here on 3.2 of complex numbers. You want to go on to your assignment, and I'll see you on the next one coming soon.